we will begin the morning session, and it's an honor to introduce Professor Helge Ruddat, who is talking about the Twistor space of the universal unfolding of the AN singularity and beyond. Thank you.
Yeah, thank you for being here this morning, 1 hour earlier than yesterday. Definitely we had less talks yesterday. So it's a bit of a bridge from the title to what I'm actually talking about. So I'll try to give an explanation for that. What I'm doing is I'm not directly looking at any particular singularity. I'm looking at them from a more categorical perspective. So when you smooth out a singularity, assume you can do that, and the smoothing of maybe an isolated singularity, AN singularity, then the Milnor fiber is a bouquet of spheres. And so I'm then taking the Fukaya category of the spheres. There have been talks before where similar things happened. And I'll start from just, beginning with having such a category and then doing stuff with the category. And we'll come back to some of the structure that you're familiar from the singularity. So kind of it's really a backwards approach to studying singularities from a different starting point, which is the category. I'll try to explain that in a moment. So the leading question I want to have in my introduction is why care about quivers? Okay, so my talk is it's quite clustery. It's quite a cluster geometry talk. So I have to motivate that cluster stuff to you. I think some of you have seen it before. But I'd like to give 3 examples why we might care about a quiver. A quiver is something like this. It's a graph with directed edges, yeah? So something like that. And so here are a few motivations that you might care about. So when you look at the projected plane over the complex numbers and you remove a smooth elliptic curve, so it can be any smooth cubic, then this complement in the de Niro style permits a special Lagrange fibration. Special Lagrange fibration. I think this way it was proved by Yusha and Lin and collaborators. And the main feature that I care about now here is that the base of that fibration is an integral affine manifold with singularities. Yep. The base of the fibration B is an integral affine manifold with 3 focusing values. And so such a thing will show up in other talks in this conference. That's why I mentioned this example. We'll have much more complicated. This is a very simple one. It's homeomorphic to R2, but it has an interaffine structure with these singularities. And then how does it relate to quivers? Well, on top of having this affine structure, it also has a scattering diagram. And Tim is an expert for that one. So it contains a scattering diagram. I don't know whether anybody's going to explain that to you. I will not. I'll just mention it. And that scattering diagram is the cluster. It can be viewed from a cluster angle. Is the cluster scattering diagram of the quiver, and the quiver looks like this. You've probably seen that before. The quiver is also associated with KP2, the canonical space bundle over the base. You have 3 arrows that go from one vertex to the next, and then 3 more going from that to the next, and then 3 more here. And then there's 3 vertices. And so that's a quiver. And associated to that quiver, you can associate a cluster scattering diagram, and that thing shows up naturally in the base of the Lagrange fibration. That relates to this quiver with some interesting geometry that has to do with Lagrange fibration. That's one thing why you might care about quivers. Here's the next thing why you might care about quivers. It's a different example. B. As I said earlier, when you have an AN singularity, some other singularity, say hyperspace singularity, you smooth it out, you get a bouquet of spheres. And because they're vanishing cycles, if you look around you, and it might have a configuration like this, and then you can take the dual dissection graph of those spheres. So in my case, I like to think of them as S3. Okay? So I would have to have a three-dimensional singularity. Yeah, you take this dual dissection graph, and the next thing, in order to have that be a quiver, you have to have some orientation on it. And there's some ways to construct that. Then you come up with a quiver. And then what's interesting is that if this the spheres, they sit inside the Milnor, whatever, the smoothing of the singularity, Y, then this bunch of spheres gives a subcategory of the Fukaya category of Y. And by those spheres.
Can I ask what rules the choice of orientation?
Let me not get into that.
Okay. Is it S3?
Yeah, I want to. Yeah, you can do that in surfaces as well. But I would like to get to Calabria 3K.
These spheres are intersecting certain
and points. So then it's a subcategory whose derived category is what I'd like to call D of Q. It's the Calabi-Yau 3 category associated to the quiver. So the 3 category of Q. So there's the path algebra of the quiver. You can study representation of that. There's a Calabi-Yau 3 category associated to that by Ginzburg. And then you can take the right category of that.
So who is Y again?
Y is the smoothing of the singularity. You think that you have an AN singularity, you smooth it out, and then you get this guy.
Smoothing out means what?
The form. Yeah, nearby fiber.
So this does work in any dimension, right?
Yeah.
Place 3.
Yeah. So that might be another thing why you care about quivers. And then from a more that's more like a very basic reason. So if you do exactly this, or you can just pick some random quiver, not maybe coming from any geometry. If you have algebraized in that sense, so you can always associate the derived category, Calabi-Yau 3 category, right? Derived 3 category of the quiver. It always works. You can mix that thing, and Calabi-Yau 3 categories are very interesting categories, maybe the most interesting derived categories. So they give you examples of that, and they give very nice examples of CY3 categories with good finiteness properties. So what I mean by that is there exist finite hearts. Yeah. So it's sometimes hard to find a heart with finitely many simple objects, but these always happen. So they're very good Calabi-Yau 3 categories to study. If you come from more an algebra point of view, that might be interesting to you. This is my singularity thing, and this is more the grounded choice vibration thing. So which are different topics that might connect us in the conference. Different angles to go. And so now I'd like to then say what you can do with a quiver once you have one.
May I ask you just quickly? I missed the arrows on this.
Yeah, I didn't explain that.
Oh, you didn't.
What?
It's not hard. It's like the thing of the collection of objects.
Yes, I can give you a reference. Okay, so this is Thomas Yao Zeidel, these kind of people. You find that in there. Okay, they measure that. So Thomas Smith Zeidel. So So there you find more details on this. And here for this one, you can also find more details. You know, for example, cross setting here. Zebra, of course. And then, you know, Tim has worked on this also some before reference. Any other, yeah, and then Yushan Lin. So lots of people. Okay, so what to do with a quiver if you have one? So many people study quiver representations. In that case, you associate a vector space with each vertex of a quiver, and then you associate maps from one vector space to another. The vertices are connected by an arrow. You can study the modular spaces. Those things are interesting things to study. That's not what I want to do. I want to do something else with the quiver. I want to mutate it around. Yeah, when you mutate it around, you can also do quiver representation of mutated quiver, but that's a very different modular space. So often people don't do that. But I would like to look at all the mutations you can do with one quiver. So explain what mutations are in a bit more detail. And I'll connect it to the story with the category. Okay, so that's maybe an interesting angle that not many people take. Like most people in the quiver world, they don't connect to categories or something. Yeah, not quite sure. Categorify that as well, like element or but maybe not caveat detail. That's maybe more Tom Bridgeland. Anyway. So if Si is one of the spheres here in example B, yeah, so you have say you have this bunch of three spheres. You have any single one of them, you can do a spherical twist in the sphere, and that will give an automorphism of the derived category. You can do a spherical twist. Yeah, so this was Thomas Smith and Seidel did that twist. I don't want to go too much detail on. Twist that in the object, and that defines an automorphism of the derived category of one. I think we also have Chet is not here, but he was an expert twists and these. Leading to a mutation. So that I want to explain. Okay, so leading to a mutation in SI. So if you have a heart in a category, you can tilt the heart to the left and a right tilt. And I want to look at this a little bit. So say you have a heart, and yeah.
What's a heart? It's like a pair of objects that would generate your category.
In some sense, yes. So remember, you have it's intersect. You have this heart means you have the complexes that start say at 0 and then the positive, and then other complexes are the negative, and the intersection of those two categories is an abelian category. That's called a heart with some properties to satisfy. It's a usual thing in derived categories. So yeah. So these are hearts, and you know sometimes these hearts are finite. So you have finitely many simple objects. So yeah, simple objects are finite, and that always happens. Those things exist always for these categories for quivers. They always have finite type hearts, and the number of objects in the finite heart are the vertices, the number of vertices. So there's one simple object for each vertex in the quiver. The story I want to get to is if you mutate the quiver, that matches with the tilting of the heart. Yeah. And what's interesting, when I get to that point, tilting a heart in the derived category, you can do it in two ways. You can do a left tilt and a right tilt. So you have this, you know, translation functor, kind of keep direction left, shift right. So height you can tilt both ways, either left or right. Any mutation in the quiver aesthetic, there's only one mutation. No left and right on the mutation. So what happens, I'm going to explain to that in a moment. The left and right become the same in the quiver world, in the cluster world. Then you go from this category perspective to the cluster perspective, and it loses the left and right orientation. I'll try to explain that. Okay, so that's I'm trying to get to that. the twist in the simple object. And then if you have a sequence of symbols, let's say S1 to Sn, symbols in a finite heart, they span it. Then you can choose each one of them to do a twist like that, a spherical twist that gives an automorph in the derived category using the simple twist. And then with that simple twist, you can cook up a mutation of this set of symbols and get a new set of symbols. Yeah, so I'm going to put this here. Mutation. As I said, there are now two types, the plus and minus. You pick one of the simple objects, like one of those spheres, and then you mutate all the other ones by an operation. I'll explain how it works. So if you have another one, Sj, you do a different set of things. You either do a spherical twist in the simple object and just apply the spherical twist to the sphere. That's in one case, I'll get to the case in a moment. Or you don't do anything to it, you just keep it. Or you shift it by 1. And what are the cases here? You shift it by 1 if I equals j. You don't do anything if a number, Bij, is less than 0. This one, I is not j. You twist it if the number is greater than 0, I non j. So what's that number? Bij is an integer, and it's the Euler characteristic of Si and Sj, and that's defined as the alternating sum for all integers of the derived hump dimension between the objects shifted. Okay, yeah. So I mean, just do that. Put the two objects, and you compute these derived humps. Yeah, that's a graded thing. Take the alternating sum, and that gives you an integer because it dimensions finite dimensions. Yeah. So that's just a rule what you can do, but it turns out why is that a useful thing to do? So
Number is never 0.
it is never 0. Wait, yeah, well, it could be 0.
The spheres don't touch each other. When it's 0, to take them away from their graph.
I think it's included here. It's 0. Yeah. Yeah, and also that other thing is that if they don't touch each other, then you don't just put it here. Right. So, and you define similarly mu Si plus, and where you switch those two rules. Okay. And so, so the point is that if the heart A is generated by S1 to Sn, then the right tilt is generated by the muse. The right is the plus. Plus guys, Si. The left tilt. All right. Yeah. So it gives you a rule to find the simple objects of the tilted heart. Okay. And And now cluster theorists have combinatorialized this category operation. So there's a parallel mutation story for a quiver, where what you then change is not so much simple objects. What you change instead is you change generators of the field of rational functions of projective space or affine space. So this is now a parallel story, but we'll connect to it in a moment. So this is more the categorical mutation stuff. We have the plus and minus. Now comes the cluster version. Cluster theories. Have a combinatorial version. Of this. And it's linked to our rational transformations of affine space, which has rational function fields that looks like this. Yeah. So it's the change of set of generators of this function field. And now I'll go into that in more detail in the next chapter. So now I have looking at the Poisson cluster X variety. Of the quiver.
Yeah. So, in the old days, I know, 40 years, there is this book by Ruddat called, are these the mutations in the context of Euclidean categories, or how are they related to those?
In
It looks like
derived
this is
categories.
sort of half of it. Sorry?
In derived categories.
Yeah, you can, but it's
Yes, but
it looks like
it's a bit special because I'm doing a Clavier 3 category. So
yeah, but you're taking the heart really. So
Yeah.
the twists are always around the heart.
and my heart is generated by this simple object has a finite dimension simple object. So it's a bit special. Yeah. Most hearts don't have finitely many symbols. And most people study more like the Fano setting. With exceptional
Right.
connections. and
But
so
then
on.
you can take the Fano and this quasi-projective total space of the anti-canonic bundle.
Yeah. But yeah,
Anyway,
right.
Sorry.
That was my. I had an example, right? I had this KP2 example, and that's an example. That's the simplest, maybe a simple example of the KP1. And then you see that derived category is quite difficult, but it does have finite type hearts. There's some finite type hearts, but some other hearts which infinite. Yeah, so we can discuss that.
One more question.
Yeah.
Yesterday we heard about the word spherical in context for monogamy.
You heard what?
How is spherical related with monogamy?
Yeah, it's the same twist. I mean, when you twist around a spherical object, that's the same. It's because a spherical object is a spherical function.
this is what's called actually the thin twist bicidal, in fact.
Yeah, you can do a symplectic Pound transport of Lagranges. If they come back to the same fiber, they have experience as well.
This is Seidel's thesis, yeah. For the Gaia.
So Q is a quiver. X1 to Xn, the coordinates on the algebraic torus, C star to the N. Yeah, also view this generated with a function field. Then I want to make a new quiver. Mutation of Q depends on a vertex. You choose. And it goes like this. Using I, it maps one of those generators to, or in fact, all of them. Yeah, you should think of this. You pick one of the vertices of the quiver, I. Quiver might be just looking like this. That's a very simple quiver. The A2 quiver. You pick one vertex, then you mutate in the vertex, and it sends all of those guys to something else. So in this case, would have two. You would have x1 and x2, and you would change them. And the rule how to change them goes like this. You send xj to xj times a binomial. Binomial is 1 plus xi, so plus 1. And then there's an exponent here. Or it's xj 1 plus xi and minus 1. Would be the same exponent. Or it's the inverse of itself. And this last case is again when they are equal. This is when they're not equal. Vij is less equal to 0. And this is j greater than 0. And so what are these things? Vij is the number of arrows from vertex I j. Yeah. So here's the simpler what the integer is. Integer is the number of arrows. If the arrows go the other way, you have a negative integer. Yeah. So the direction gives you the sign. And then you just form those. It's a rational transformation. Yeah? If you map all your coordinates under that rational transformation, it's set up in a way so that if the original things were a set of generators of your function field, you map them all over. They're again a set of generators of function field. So you're mapping a set of generators of function field to another set of generators of function field. And the interesting, what you then want to do is you want to iterate that. You do this again and over, and then you get more and more complicated expressions here. Yeah, you iterate that. But each step you will still have a sequence of generators of function. And now that's sort of the basic beginning of cluster geometry. The cluster algebra or Q, defining this now, is the C subalgebra of the function field generated by all these expressions. Generated by all expressions from iterated mutations. UI, yeah, like UIJ, whatever. You not just do one I, you do several. You combine I and J. Okay, just
They're the same.
yeah. When it's 0, then it's, nothing happens there. And so now there's you can now, it's interesting, you can go back and forth between these two different pictures of mutations. But there's still this mystery of that the one sort of mutation has a left and right version, whereas the other one is not. So here. But yeah, so this is the algebra, the cluster algebra, it's algebra. Yeah, you can take spec of the algebra, then you get an affine scheme. But and it's closely related to what I want to do. I don't want to do spec of this. I want to instead glue algebraic tori using those operations. It's not exactly the same as spec, but it's closely related. So the cluster algebra, spec of cluster algebra is the affinization of what I want to make. I want to make XQ. So XQ is the cluster of Poisson. Poisson cluster X variety. So in cluster geometry, there are two cluster varieties. There's an A and an X variety. I'm talking about the X one. Yeah. Most times when you hear about cluster geometry, you first hear about the A one, because A has more examples or something. But I'm doing the other one, the X one, and they're distinguished by the X one has a Poisson structure. A one does not have a Poisson structure. That's this one I'm talking about. And how do you get that? So you get that from these mutations. Okay, the A variety has different mutations. They look different. Yeah, so this is the X-type mutation that I look at. What you do is you take a copy, of the algebra torus for every mutated quiver. Yeah, so you start with the quiver, you mutate it around in all possible ways, like infinitely many. Typically, it's infinitely many. And then for each quiver that you get from the mutation, you put this copy of this. And mind you, when you mutate it around, you keep track of those expressions. So it's not just the quiver. If you mutate this guy around, there's not much happening. I didn't explain what it does combinatorially. So you get a new quiver and so on. That's just because quivers on two vertices, they're finitely many. Yeah, in fact, if you take any finite number of quivers or vertices, combinatorially, there's finitely many quivers you can make from them. But you not just take that quiver, you decorate it with those expressions, and that makes it infinite. Yeah. So once you decorate that with these variables, from those you can have infinitely many different ones. Typically, when you take a random quiver, you get infinitely many of those. And so, but you consider these quivers different if the expressions are different. Yeah. So quiver with decorated expressions, you mutate around as much as you can, and take then one copy of C star in the end for each of the things you get. Typically infinitely many, and then you glue those copies under these maps. So whenever one quiver mutates to another one, you glue those copies of C star to the end under the transformation, under the ration transformation. It's not even defined everywhere, right? So if xi is -1, then I have a problem because not a map from C star to the end to itself. Yeah. So it's supposed to be, it's a birational map. A rational map from C star to itself. But you glue them, take the quiver, glued along. So there's an open subset of it where it is a regular map, and you glue it to the other thing was a regular glued along the mutations. Yeah. So that gives you a scheme. Yeah. May not be finite type because it may have been the scheme. You can call it variety, cluster X variety. Irreducible. If it's connected, it's a connected thing, then it's reusable. And so what's going on is that this is a scheme, and now if you take at the affinization of the scheme, so you take global sections of the structure sheet of it, you get the cluster algebra back. Yeah, so that's why this is an affinization. Okay, that's the basics of the cluster X variety. So let me get to the subtle point. Which is we have mu I plus, mu I minus in CY3 category, but only a mu I in cluster X variety. Yeah. So how is that being explained? So what you can now do is you can form what's called the cluster exchange graph. So let me do that.
Are you gonna tell us what Poisson is? No.
I would like to skip that. Also.
Okay.
Yeah. There's a Poisson structure on this coming from the skew symmetric matrix coming from those VIs. Yeah. So these VIs, if you put them in a matrix, they form a skew symmetric matrix simply because of this arrow feature, skew symmetric, and you use that matrix to write down a skew symmetric form on the cotangent sheet of this. Yeah, tangent sheet. Then you have a Poisson structure. You can also apply to functions. Yeah, all right. So so what you do is you make a graph from all the quivers and all the mutations. So every quiver with those decorated functions gives you a vertex on the graph. And then you mutate it, you make an edge from that vertex to another vertex to the mutated graph. Yeah? Just produce a graph. It's a tree. Yeah? You make a tree. But then if it happens that at some point, under different sequence of mutation, you get the same quiver with the same decorated guys, you then identify them. And so it could be finite in principle if something's happened to be the same after a bunch of mutations, and then you do identify them. That's the cluster exchange graph. Yeah, so the cluster exchange graph is all the mutations that you can think of. There's a vertex for each quiver. So let me just put this. That's a graph you can make. And then there's another graph you can make. And that's what's called the tilting exchange graph. So you do a similar version with the category version. Tilting exchange graph. But here you have even more operations because for each mutation you have two vertices, you have a plus and minus. And so it gets double as many edges. From every vertex, there are double as many edges. Using E1 plus Y minus. But then there's a surjection, yeah? So you can simply you just identify the two. And so when you go from one vertex by the mu I plus, mu I minus to another one, plus mu I minus, then down here, you just do this, you just have one. And so you map that to here. So these two get identified here, and they just get identified. And so there's a map of graphs like that. Yeah.
Do you use the graphs or the decorated graphs?
The decorated graphs. Yeah, but you know, it's bit.
The decorated tilting exchange.
Yeah. Yeah. Well, the vertices are decorations, yeah. So the graph itself not so decorated.
Yeah.
Yeah.
So when there's these kind of like weird the things that I know of, like for instance, when in the threefold we have some sort of like almost like vibration, let's say, and this kind of like corresponds of like mutations of these legs coming from the negative kind of right, the mutations that coming from singularities, that is nodal times
Yeah.
x1.
Yeah.
Right?
They look like this, yeah.
Yes, they are the ones that look like this.
Yes.
And then you build part of your mirror by doing this chart.
Right. Yes.
You don't go.
Yeah.
Can I, where is the Lagrangian spheres? The Lagrangian trees.
Well, I was hoping that you could tell me.
Okay. Perhaps it has to do with the Lagrangian sphere, and Dio and Mac got out of this.
Yeah. You know, it's not fully like I don't fully know how to connect all the stories. Yeah.
Oh, I
Yeah.
see.
So
I mean, okay.
I know it. I can have some partial answers to it. You know.
Yeah, I know Chris on the lower dimensional thing that he knows how to get the AD singularities, and I know he knows precisely what almost all vibrations then, and I know how to see them, and I know how to mutate them.
Okay, cool. Yeah, maybe you can have better
dimensions.
Yeah.
But
Let's talk after this.
yeah,
Let's
okay.
have some more on thing on plan. So this is it's not really a very, but you can do this. It's something you can do. And there's a lot more to say, and I should give references and so on. But one extra thing that's important, maybe. So when is something finite? Yeah, so that's an important thing. So because you might have an infinite type scheme versus a finite is much better. So there's a theorem by Foreman Sivelevitsky. And it says the cluster exchange graph, so the one here, but then the other one is also cluster exchange graph, is finite if and only if the quiver Q is mutation equivalent to an orientation of an AD quiver. Yeah, so that means it's finite if and only if it's possible to mutate that Q around, so that at some point it looks like one of these typical ADE things with some orientation. The arrows, the direction of the arrows doesn't matter, but it has to be one of those ADE guys. Okay, yeah. Among all the possible mutations, there must be something that looks like that. Then it's finite. Zero. And so the construction I'm trying to do in this class, that they will use that finiteness assumption. I mean, if you do the example B with the Milnor fiber, that's automatically finite. Yeah. So, but if you do the KP2 base, what you wanted to do, it typically is not. Yeah, those things are not finite. So the example A is typically infinite. The example B is typically finite. So what I want to make a bunch of spaces.
So the example B is typically finite even if you didn't have an ADE configuration of spheres.
No. Yeah, well, no, maybe not. Yeah. No, probably. Okay, yeah. So no, yeah, you're right. If it's finite only if it's 80. Yeah, I agree. Yeah. So I've made one space, yeah. I've made this cluster X variety. I want to make at least 5 more in a similar fashion. So in fact, one more I can already tell you. So it's something like a positive real.
I do not understand what's on the table quiver. You're just changing the
I didn't explain it.
decorations.
No, you also change the arrows.
Oh.
You have the same number of vertices, but you change the arrows. So there's some rules which I didn't explain. Yeah, I skipped over this. So sort of, yeah. Yeah, you mutate in the vertex, yeah. You change the direction of the arrows to go in and out of the vertex. But that's not all you do. You also do if there's an arrow going in and out from that, so that's a vertical mutate. Then instead you put one here. You concatenate. You know, yeah.
So are you allowing loops?
No, not like loops. Yeah, no loops in that. Yeah. So the positive real cluster space, that's the easiest one to explain. You just take the positive real points in. You do this as a subset and C star. Yeah. Yeah. So the positive real points form a subset, a submanifold of half the dimension, half the real dimension. And you do the same mutations on that, and the operations preserve those sets. So you map from, you just assume all your xi's are in that subset. Then after mutation, they're also in the subset. And that's because of the positivity, right? If you have a positive real number, you add 1 to it, still positive real. You multiply with it, also positive real. So it preserves these operations. So you know it gives you a subset. So then UI preserves subset Ri, so R greater 0 n. So you have a map from one to the other. And it's even better, it's not just preserve it, now it's biregular. So all the bad points where you can't evaluate it's just birational, they have negative values. Yeah. So when x, you see it, when xi is negative, then you're problematic. But on the positive, it's actually biregular, so it's even better now. So it has an inverse, biregular. Not just biregular, it's biregular. It's really fluid. And then you get a submanifold of half the dimension. X XQR plus X Q. Now sometimes I call this also C. One here, make this. Yeah, just call it X. Yeah, let me just make this. And so we have the submanifold. And I want to make more of those. The next one I want to make is stability space. Stability. Yeah, do that works a bit more general than I need.
R plus Q alpha to R. That's with zero to the end.
This is a biregular map, so it has an inverse. What's the question?
So X R plus Q is isomorphic, so it's covered by only one O. Because
Yes, because of them. Yes, that's right. Yeah. So yes, it's true. Yeah. Because biregular and bijective, yeah, in particular. So you just need a single guy of them. That's, yeah. So it's homeomorphic.
It's actually just a copy of.
It is. Yeah. You can use. Yeah. It's true.
Zero embedded
Yeah.
X Q canonical.
Yeah, that's right. Yeah. So it is isomorphic space. And in many ways, like for each quiver, there's one way to have it isomorphic to that. Yeah, not canonical. Yeah, makes sense. But yeah, it's a clever observation. It's true. Yeah. So Tom Bridgeland famously defined a stability manifold for a Calabi-Yau-3, more generally for the derived category, but in particular was Calabi-Yau-3. That the manifold of the Bridgeland stability manifold. And then there's a subgroup of the automorphic group, subgroup generated by spherical twists. Yeah, in simple objects. Yeah, so these Dane twists that we talked about. Give you subgroup. And it acts on the stability manifold. So when we now have a quiver situation, when D is the derived category of a quiver, define S of Q to be this Bridgeland stability space, divided by the break group action. Yeah, so it acts on it. You can take a quotient, the break group quotient. And taking this quotient is kind of important in order to have this left and right tilt be identified. This is another space I want to make. I want to get back to it because it also has a combinatorial description. This is an abstract definition. But more importantly, I can also make it by gluing things like I did here. Keep that one. Tell me how I'm doing with time. 5 minutes. So you do H is the upper half plane. In C, yeah, with boundary. And then you do mutation, gluing of that. But now it's more like gluing of the CW complex. You do take a copy of A to the N for every quiver. In the mutation in the exchange graph, you know, vertex in the exchange graph. And then you do you glue a part of the boundary component. So this means that the WI0, or the imaginary part of WI0, we glue this with a map UI to partial I HN. And that goes like this. UI sends WI to Wj plus Wij Wi, or J, or minus this, and get the same, equal, not equal, here the real part of Bijw is greater than 0, here the real part, Bij Wi is less than 1. So this looks like ui plus and ui minus on the K theory of the drive function. And so if you evaluate it with the spherical twist, or this mutation that you took up from the spherical twist is doing on the K theory, it looks exactly like that. So these are the coordinates in the upper half space, yeah? So now it's a bit different. We're not gluing open sets. It's not a map on open sets. It's only a map defined when the real part, when the imaginary part of I is 0. Yeah, so the imaginary part of I is 0. That's a boundary component. So in a sense, you can think of you taking this upper half plane, and you're taking another one here, and you're gluing the boundary. Yeah, you just glue this boundary here to the boundary here. It's more like a cell complex gluing, very different from the gluings we've been doing before.
This looks like a complexification of what happens in the base diagram.
Base,
Base
yeah.
diagram of
Yeah, we'll get back to that. 10 minutes. So, and now, let me connect the dot here. So
you're creating a book, right?
yeah, that's a good intuition.
This book has shown.
And now, there's another space, lock cluster space. And now we do also glue h to the n copies. Also in the boundary. Now the method is wi maps to wi plus Vij log of 1 plus e to the plus wi, and 4 and plus Vij log 1 plus e to the minus ij, or minus them. Okay. Same conditions, yeah. I'm not writing this, the same conditions behind this. And that's the log cluster space. If you glue this together, you get L of Q. So here I've made X of Q, if you said somewhere. Yeah, so this is X of Q. Then I've made S of Q. This is S of Q. What's the name for that? Well, it's the same as that over there. It's the same. This is a combinatorial version of this, yeah? So here there's an abstract version. You start with splitting manifolds between the quotient and the break group. But then there's a combinatorial way to describe that. It's a theorem that gets you the same thing. The theorem. And then there's also a log version of this. How do these things relate? Relate because they're all part of a Twistor family. But that's sort of the upshot. I can end my talk on that note. So the final thing in the talk will mention a tropicalization process. You know, that's kind of novel. I think nobody of you seen before it, that tropicalization can be a polymorphic family. Really cool. Many of you have seen tropicalization before. So something like this. When you do this function, yeah, so this is the function epsilon times log of 1 plus e to the w over epsilon. Yeah, because epsilon is the w variable, the graph of this function. And then there's graph another function, which is the max function here and then here. It's a piecewise linear function. This is max of 0W. Yeah. And so this one goes here, and the epsilon goes to 0. That's not magic. That's kind of like easy. But the cool thing is now you can do this with the gluing. So here's the log cluster space. You put an epsilon in here. Yeah. You put an epsilon here and here. Okay. And then we take the limit. You go to this guy. Yeah. So this is epsilon goes to 0. You end up with the stability space. The log cluster space can be put in a family with this epsilon, and then at the limit, and the cool thing that even works with the holomorphic epsilon. Works with the holomorphic epsilon. Get that limit. And how does it relate to this other one? So that's then the next thing you can do on the upper half plane. You just run the exponential map on each component. It's a very stupid map, yeah? So you take Wi, Wj maps to map x of Wj, which is the x. Okay, yeah, so you just do this. And that defines a continuous map from LQ to x of q, continuous, canonical. And that's the theorem that this is a no, is a local homeomorphism. Yeah, this is Bridgeland and myself. This map a local homeomorphism, which has the advantage of then this is a complex manifold, complex variety, as a complex structure. And so it gives this one, gets one. Yeah, so this gets the complex structure as well. So it's a local homomorphism. You can pull it back, get a complex structure. So you have a complex structure, then you put it in this family with the epsilon, and then you take the limit, you get the stability space. And that's a Twistor space construction. So we've made a Twistor space Z of Q, the Twistor family, over, so far it's over C, eventually want to make it over Q1. So this is a hyperkähler story that you cook up around any quiver. We need finite type so far, but it's like a version of a nonlinear Frobenius manifold. Frobenius manifold you have in the universal unfoldings, connected back to my title. This is a nonlinear version of Frobenius manifold. Yeah. Time, you can ask questions.